Welcome. This week, you might feel like you have Bayes for brains, but hopefully today we'll learn that Bayes is for brains. The topic of this week and this particular lecture is how to do probabilistic reasoning that will enable us to understand what the brain should compute and potentially what the brain does compute. So first off, who is your instructor? I'm Paul. And this is Zach. But what's happening today? What's happening today is we're going to try and explain why Bayes is important for the brain. And our lessons will look at how to combine probabilistic evidence. We'll focus on probabilistic models for variables relevant to behavior. We'll look at how to fit probabilistic models to behavior, and we'll look at the importance of weighing risk. And in our outro, we'll see that there's an exciting future for Bayes in the brain. So what is the motivation for studying Bayes? It really boils down to normative models, which I'll explain in the next few slides. The role that a probabilistic normative model will have, and hopefully we'll have a few good examples of that. We're going to show you some foundations, learn about how to think about random variables, probability inference, and we'll preview the lessons of the day. We could call it fun with Gaussians if you think those kinds of things are fun, which of course I do. So normative analysis is really the cornerstone of Marr's 3 levels of analysis, which you probably know are computation, representation, and algorithm and implementation. The highest level of Marr's 3 levels of analysis handles the kinds of things that the brain needs to do in order to survive, to reproduce, and to find and eat food, to forage. So basically, what problems does the brain solve and why? Those are the computational level problems, and that's our focus for today. We'll also, though, see that once we hit the computational level of analysis, there are deep applications of normative analysis in that it gives us key insights into the kinds of representations and algorithms that must be used by the brain, and also puts constraints on what the brain must do to achieve the computations. So what is normative modeling and why is it important? Well, normative modeling describes the task that the brain undergoes in and of itself. It gives us guidance about what to expect from behavior, what an animal should do. It gives us a benchmark for judging performance so that we know if something is actually as good as it gets or very, very far from as good as it gets. But it doesn't answer how-to questions. For that, you should probably go see Randall Munroe's how-to. So normative modeling is something that's easy to illustrate the importance of from a couple of examples. In this example, we have the lens of insect eyes, which are compound. That means they have many different tiny lenses called ommatidia. And the ommatidia sizes and number are constrained with respect to each other in a way that you can show is optimal. Barlow first showed this in 1952, demonstrating that the diffraction limits on lensing for each of the lenses is counterbalanced by the advantage conferred by having many of these lenses in a way that this trade-off fits exactly a theoretical optimal. Even more interesting is that behaviorally, we can detect down to a single photon of light. And what this really means is that our behavior is fundamentally no more limited than our ability to absorb a single photon in our cones. So normative modeling in this setting provides us with an absolute bound on what can be achieved, and there's really no wiggle room for the brain to mess that up because we're achieving essentially what we absorb. So why probabilistic normative models? Well, fundamentally, the world is uncertain. You don't know everything that's out there. So as an example, if I gave you a Bitcoin and you know that a Bitcoin is more likely to come up heads than tails, then you can play the odds and do better. And if, more importantly, you know that Bitcoin is going to go up rather than down, then you can invest and do better. In general, the fittest brains will use probabilistic reasoning. A probabilistic normative model says how an animal should draw inferences, and this is a useful benchmark for judging animal behavior in brain computations. So, why are we using probability? What probability does is it provides a language that allows us to relate things that you can observe directly to things that you really would want to know about. So in this example of Plato's allegory of the cave, you directly see the shadow on the wall, but you kind of want to know about the guy behind you that might be doing something dangerous. In general, the world provides us with a set of signals, which are a reduced sensory input that is indirectly related to the things that we really want to know about. So the world and its properties must be estimated in the brain using a kind of model for the relationship between what is sensed and what's out there in the world. And this process is well modeled or well represented by probabilistic reasoning, as you'll see today. The interesting thing is that the ideas that we're looking at and their importance are fairly old. They were first realized by Laplace and Bayes, who recognized that both uncertainty occurs, it's ubiquitous, and you can use a reasoning strategy to overcome it. Now, why is the world uncertain? The world is uncertain because we don't always have the data that we need, like I was showing you in the previous slide. In addition, there is fundamental stochasticity or noise in the world, which limits our ability to accurately measure the things of interest. And finally, during this estimation process, the estimation process that we employ has to make assumptions which are often wrong. So what do I mean by uncertainty from missing data? Well, you can see the shadows on the wall, and you'd think, based on those shadows, that there are a couple of people who would be sitting in chairs, rather than a rather complex and interesting art exhibit. But there you have it. What you're looking at on the left here is the same picture as on the right, just at a different amount of time for exposure. And what's being revealed is the fundamental stochasticity of light, in which photons are coming at a camera randomly. This doesn't require a brain to inaccurately or stochastically sense, but that's happening too. All of these processes, these physical processes, introduce stochasticity, which results in uncertainty. Finally, as we try to take our evidence and use it to make inferences about what's out in the world, the fact that we may not have an accurate model will generate errors. If we understand that there are errors, then we can understand also that our estimates have uncertainty. They aren't perfect, and we can understand and compensate for that. So what I'd like to do is walk through a few motivating examples that explain why probabilistic normative models can be important in the entire perception action cycle, starting in perception, going through cognition, and motor control. What you're looking at here is a very famous example of your brain trying to sort out what's going on in a luminance profile. The luminance profile is described by a very simple function. It starts high at the left edge. It is a linear function with a step in the same linear function. What most people see on the left-hand side is a flat surface with two different paint colors, whereas on the right-hand side, the very same luminance profile is seen as a change in shape, in which the variation in lighting is being attributed to the interaction between a shape and the light direction, called shading. This example shows that the inference that you're making from the world is one that isn't direct. Moreover, interestingly, this example is one of the best cases for using Bayesian reasoning. In cognition, we often have to learn about what a category of something is. And often we need to do that from just a few examples. This is very much unlike cases in which we have lots and lots of data in machine learning, and we learn a function exploiting the fact that we have lots and lots of data. Here, if I give you only a few examples of a tufa, I bet you can pick out 2 to 3 other tufas that are in this list. Finally, as a motivating example, action problems have uncertainty and probabilistic reasoning in several different, very important places. Perceptual and motor errors generate uncertainty about where we would like to target our actions, like swinging a racket. Moreover, noise in the sensory and motor systems, time-varying properties like muscle fatigue or stochastic sensory delays can result in uncertainty about the outcomes or the course of our action. More subtly, the motor system can achieve the same result in many different ways, generating uncertainty about what plan we should take to accomplish those actions. In all of these cases, probability theory plays a critical role. Now, the question is, what is probability theory? And now we turn to foundations. So what is probability? Probability measures the occurrence of events. In a subjective sense, probability is the belief that an event occurs. But in an objective sense, or a measured sense, the frequentist sense, it's the frequency with which you observe an event occurring. Both of these ideas, subjective and frequentist, are really important as foundations for probability, but we'll mostly use the subjective sense throughout today's lectures. One of the most important concepts within probability is that of a random variable. Random variable is a variable which takes on values over a set of events. For example, for the 2 die that you see in the picture, the dice show particular values. The events are different sides of the die coming up. The random variable are the numbers or the values associated with that side up. What a random variable allows us to do now is write down an expression like the probability that die X takes value 1 is 1/6. There are 2 weird rules of probability that, if you know them, you can derive the rest of probability theory. Both of them involve what you do with logical combinations of events. So if we have 2 events like die X taking on value 1 and die Y taking on value 1, we'd like to know the joint probability of both of those occurring. If they're independent, then we can compute that probability as the product of the individual event probabilities. Now, if we're interested in an OR over the values that a random variable can take on, like the probability that die X takes on value 1 or 2, then we can sum these probabilities. The product rule is particularly important, and it has a common shorthand that you really need to know. So when you look at an expression and you see the probability of X comma Y, you should think probability X and Y, and that's called the joint probability. For independent random variables, that joint probability is the product. So as an example, what's the probability of double 1? Well, it's the probability of X 1/6 times the probability of 1/6, 1/36. The sum rule tells us what we should do in order to compute the probability of ORs. As an example, what's the probability of an odd number occurring? That's the probability of x1 plus x3 plus x is equal to 5, which is 3/6. The interesting thing about the sum rule is that we can use it to understand how to ignore one variable in a collection of random variables by ORing over all of the values of the variable we are interested in. As an example, what's the probability that the first die shows 1, not caring about the second die? If I give you the joint probability on x and y, we can take those values and OR them together like shown. The probability of x1 and y1, or x1 and y2, and so on, is then equal to the sum of the joint probabilities that x is equal to 1 for all of the values of y. If we were to put all of the joint probabilities into a table, what we're doing is summing over the column indicated in red. What we get out of it is 6 over 36, which, of course, is 1/6, and it's just the probability that x is equal to 1. And that shows us something rather special, and that's that when we marginalize or we OR over a random variable, we essentially eliminate it and we get back the probability of an individual variable or a collection of variables. We call this marginalization because after we compute the marginal, we can always write that down in the margin of a joint probability table. One of the more interesting things that we can do is we can also compute the probability of something more complicated, like x plus y is equal to a value like 4. To do that, we can see that we're doing basically the same as marginalization, but instead of moving along a column, we're moving along this diagonal, summing each one of those values. And we can show fairly easily that we'll get 3 out of 36. One of the most interesting things we can do with probability theory is called conditioning. What conditioning does is it allows us to take advantage of things that we know in order to reason about things that we don't have direct access to. So as an example, imagine that somebody throws a pair of dice and you hear that it comes up 4. But now, what you really want to know is what are the values of each of the individual die. We can, if you're interested in the value of the die x, we can write that down as a mathematical expression shown. The probability of x given, you know that x plus y is equal to 4. Well, interestingly, we can now just write out all of the joint probabilities along that diagonal, those red lines. And for each, we can figure out how many times x comes up 1, which is 2 times, how many times x comes up 2, which is 2 times, and x comes up 3. And each one of them is then coming up twice out of 6 possibilities, which means that they all have a probability of 1/3. What's interesting is that the same ideas that hold for tables extend to continuous random variables. What I'm showing you here is a 2-dimensional plane, which is the appropriate place for a joint distribution on the set of points x and y. The orange shows us a density function, which gives us the relative probability for each point in the plane. The blue distribution shows us the conditional distribution. So for a particular value of y, we get the probability of x as a slice. Notice that it's renormalized. Renormalization takes into account the fact that if we're conditioning on y, we know the value of y, we need to divide through the joint by the value of y in order to focus on the probability of x. And finally, The marginal probability can be defined essentially the same way as the sum over y of the joint distribution. However, whenever you see an expression like this, we're using sum, but we really mean integral. So surprisingly, or maybe not surprisingly, we can apply just the basic rules of probability and the operations I've shown you in order to manipulate probabilities and understand how observations should affect our subjective beliefs. And that's the core topic of today's lessons. It's actually important that you digest a few bits of terminology. We're going to be interested in a variable x, which we don't have direct access to. And I'm going to give you a probability over x. What this probability represents is a prior understanding of how likely different values of x will occur. So for instance, in our shadow example, the various kinds of shapes that might generate those shadows, you might think that actual people are a lot more probable than an art installation. But this is a perception study, so maybe you don't. The next bit of terminology is a likelihood function. The likelihood function is a conditional, but it's a particular conditional. It's a conditional of the thing that you have access to, or the measurement, given the thing you really wish you had, x. What the likelihood function does is it provides a model for the relationship between the measurement and the variable of interest. Here, the width of the probability of y indicates something about the measurement stochasticity, because a particular value of y is not telling you everything that you need to know to determine x. Finally, the posterior is the distribution we're typically interested in to make an inference. The probability of x is our belief about the variable of interest given the evidence that we might have in the form of a particular measurement y. Those three functions that we saw in the previous slide, prior, likelihood, and posterior, are related to each other by something called Bayes' rule. It's common to rewrite the variables x and y in the form of h and d so that we can be more concrete about what role y typically plays and x plays. Y plays the role of data, and x plays the role of hypotheses we have about what's out in the world. So here, the probability of our hypothesis given data is equal to the probability of our data given our hypothesis. That's our measurement model, times the probability of our hypothesis. That's our prior understanding. The divisor term here is something that turns out to be exactly just the marginal over the likelihood times the prior. So that in order to compute the posterior, you only really need the likelihood and the prior. What Bayes' rule is really doing is it's allowing us to convert what we know or what we're given, data, into something we don't know, what's happening out in the world, the evidence for a hypothesis. In order to make decisions, though, it's not enough just to have a belief about what's likely out in the world. We also need to know what out in the world we value. We can do that by having a numeric measure of how much value we attach to an outcome. And there's a lot of different names for it. The most typical names are utility and reward. What a utility function represents is a relationship between the subjective value that you have on an outcome as a function of an objective measure on that outcome. So on the left-hand side is a curve that's typical for money, where you either gain money or you lose money, and the subjective measure then says, I like more money and I don't like less money. but it's not a direct function of money. The right-hand side is actually a measured value utility function on monkeys who are receiving juice as part of a decision-making task. And this provides you with a measure of how good to the monkey different amounts of juice incentivize the monkey's actions. We pull together value and belief into decision theory. Bayesian decision theory describes a normative framework for how we should make decisions. We should make our decisions and our actions in order to optimize the value, incorporating whatever uncertainty we have about outcomes. So what we're looking at is hopefully a fun little decision problem, or possibly a very scary decision problem. This person has decided to make a great leap into the unknown, presumably under the belief that that isn't a gaping drop-off. So how do we think about the problem of deciding whether to jump or not? Well, in a Bayesian decision analysis, there's almost always several key components. The first is the action or the choice that is the heart of the decision. Here it's whether or not you want to jump and how far you will jump. So we'll call the action the jump distance, and I'll give it a variable a. The second thing is the outcome that has value for the decision. And the outcome of most interest is whether you land your jump. So we'll say that you either land it or you miss it. And finally, there's typically a context for a decision which changes potentially the utilities and the chance of an outcome. Pulling these together will compute the expected utility for an action given the context and the uncertainty you have about the outcome. So what you're seeing on the right-hand graph is a probability that you'd land as a function of the action that you have to take, the distance that you have to engage in order to land successfully land. And on the right-hand side is a made-up utility function that could govern what subjective utility this decision maker might have if they landed the jump or if they missed the jump. Combining these together gives us a way of deciding whether or not this jump is worth it. Even though everything we've talked about so far has been normative, the Marr's level of analysis comes back, and Bayesian analysis is proven to be useful not only as a computational analysis of the best way to solve a task, but there are a number of really compelling examples that show that behavior is well modeled as being roughly optimally Bayesian. And the closer our behavior is to optimal, the more that we know that the behavior is being generated and represented in ways where probabilities matter, and the computations that are the core of Bayesian inference must be somehow implemented in the brain. And that actually then puts constraints on the implementation level as well, because the brain must implement whatever manifests in behavior. As a summary of this intro, the core concepts we hope that you have at this point is latent variables. Latent variables are things in the world that you don't directly observe, but may be of critical need or interest to an organism. You should understand what sensory evidence is. That's the stuff that the organism has direct access to through its sensing apparatus. Probability is something that provides a measure of our uncertain beliefs about what we think will happen in the world. And inference is a computation which allows us to quantify the probability of these latent variables from evidence. Utilities and rewards provides us with a numerical measure of the subjective value of outcomes of interest. And decisions and actions are the key thing that we're really modeling in behavior. It's the choices and interventions that an organism makes on the world in order to obtain value. Well, we hope that you will enjoy the Bayes for brains and that your brains will all be able to do Bayes.